Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We have been discussing nonlinear sigma models, and the idea is to try to describe a system which has, let's say, broken some symmetry and use the Goldstone modes as a way to describe it. And what this does is it uses a unit vector n component as a field, and that gives you the nonlinear constraint that it has to be a unit vector, and that causes all the interesting physics as well. And this is described by a dimensionless coupling constant which is equivalent to the absolute temperature. So the main result of the renormalization group analysis that we did in the last lecture is that in spatial dimensions 2 plus epsilon, there is a stable low temperature broken symmetry phase when n is greater than or equal to 3. So something like the Heisenberg model will fit that well. And the one loop renormalization group actually provides you a critical point. You can even characterize the critical properties with this. In one dimension, the symmetry broken ground state is unstable for any n. This is something we already knew. In d equal to 2, this coupling constant g is marginal at tree level, and for n greater than 3 it is relevant, pointing to something like Mermin-Wagner theorem stating that you cannot have a broken symmetry, broken continuous symmetry in d less than or equal to 2. In d equal to 2 and for n equal to 2, g turns out to be marginal even at one loop level, which is the subject of today's lecture. What is the story of n equal to 2 in d equal to 2? This is what we would like to address. So the main ideas that you will want to take away from this lecture is that in addition to all the different things that we have studied, it turns out that there is one more kind of phase of matter, if you wish, called algebraically ordered system. Okay, so we will see what that means. So the other important thing is the idea of what are called topological defects, and how topological defects can give rise to interesting phase transitions. And most interestingly, you will see an example of a continuous transition without any symmetry breaking. Okay, so this, as you can see, is already fairly variety of new things here, and so let's move on and see how we get to those things. Okay, so now imagine that I have some lattice that in which I'm putting xy spins. Xy spins meaning spins that can move only in has only two components. So that's why it's called xy. You don't have to think of this as x and y coordinates. It's xy in the ON space. And so the way we can do that in two dimensions is you can characterize the spin by an angle relative to some spatial angle, or actually in fact we are attaching the ON direction to the spatial direction. Right? Okay. So we can sort of give the configuration as a set of theta i's. So in fact, what you can do is you can imagine that there are these two component unit vectors whose components are cosine theta I and sine theta I, or equivalently you can think of these as unimodular complex numbers. Si is equal to e to the I theta I, because the real part of this will be cosine theta I and imaginary part of this is sine theta I, and we have made this connection between O2 and U1 quite a while back. So how does the symmetry act on this? So if you do O2 rotation, you have to give me some angle associated with the O2 rotation, and what that will do, it will change all these theta i's to theta I plus theta, and then you take this and stick it back into this vector or this complex number, and you will get either a new vector or a new complex. So this is how the O2 symmetry acts on my degrees of freedom. Now I want to write down a very simple O2 or U1 symmetric Hamiltonian associated with this. So give me some configuration C, which means you'll be either giving me a set of theta i's or the vectors or whatever. You introduce a coupling constant called as some exchange coupling like J, and then it is 1 minus cosine of this quantity. So this is the form of the interaction. If you write it in complex numbers, it will be just real part of this, and you can see all of these are the same thing. We will find it particularly useful to use these complex ways of doing things. Okay, so we have introduced this. So natural question to start is at 0 temperature. We can solve this problem exactly there. So what is the ground state? Ground state will want to have all the ON spins at every site pointing in the same direction. So you can choose some direction which we can call n in the ON space, or you can choose some angle theta and say that the complex number at every site is e to the I theta, and these two things are defined equivalently. So this n will be this cosine of the script theta and sine of that script theta. So this is the ground state. What about excited states? So now what I can do is I have this spins pointing in a certain direction in every site, and I can go there and just perturb them very little, ever so little at these sites. And you can easily see that if I were to say that theta I is something like this theta plus some small deformation phi I, and I were to make a continuum approximation, that is what I am doing is I am going to take this thing. So if I write this, this will be cosine of theta I minus theta I plus delta, delta is either x or y, minus theta I. If I make that small fluctuation approximation, this will become phi I plus delta minus phi I, and cosine will, when I do 1 minus cosine, I will get something like half of phi I plus delta minus phi I whole square, which when I go to the continuum limit will go to a gradient, and that is how I can write down this kind of energy functional for the small deviations. And you can see that this will immediately give rise to, we have done this kind of calculation before. You will see that this will give you some kind of gapless modes, and the dispersion of those modes will go as mod k. We have discussed this when we discussed phenomenological theories. Okay, but you see, in this whole game, we assume that the excursions phi are very small from the broken symmetry value of the script theta. What happens if you allow phi to be arbitrary? Then we can still continue to discuss this problem in the continuum framework without going back to the lattice, but it turns out to be useful to discuss this in the context of using the formulation of complex numbers. It's not necessary to do this, but it becomes convenient. So what I will do is, just for simplicity, it's not anything that is restrictive. I will set this theta here, this theta to 0, right? So I will set this to 0. So I'm choosing the broken symmetry state to be along the 0, along the one direction of the O2 space. And the continuum field, any configuration, can be described by e to the I phi of x. Phi of x is the deviation from 0, which you can just take it to be, you could have called it theta of x, but since we are thinking of fluctuations about the ground state, I decided to hold it as phi of x. Okay, so now if I ask, where does S of x live? What are the objects S of x? S of x are unimodular complex numbers. So unimodular complex numbers, if you think about it, will live on this on a circle. They are points on a circle. If you think of the real and imaginary parts of the complex number as two axes, then the unit circle in that space is the point on which this S of x lives. So in this game, this is called as the target manifold. The manifold is the S1, called the circle S1, and a field configuration can be thought of as a map from my arena, which is continuum d-dimensional or two-dimensional continuum, to this manifold. Okay. So if I use periodic boundary condition, my arena I have identified the ends of my square lattice or whatever I had, I put periodic boundary conditions and I am identifying these two and these two, so it will become equivalent to a torus. So this field configuration, any field configuration can be thought of as a map from the torus to the circle, right? How do I think about this? So there is a point x associated with each point. I am giving you a complex number s of x, which is written as e to the I phi of x. So it's described by something living on here. So field configuration must be thought of as a map from the torus to this. So now I want to characterize the excitations in the system, namely I want to characterize this S of x fields in a certain way. So to do this, I am going to introduce a device. So on the torus, which means I have a sheet in, I am going to draw a closed curve which I call C here, and there is an expanded version of the C drawn here. And what I am going to do is, you have given me this S of x field. So at every point x on this curve, I know what is S of x because you have given it to me. So what I am going to do is, I am going to compute this contour integral. So I am going to start from this point x here. So that's the starting point. I am just going to go around the curve like this. I am going to integrate. I am going to integrate this, and I will end up here. So now you can, it's a very simple exercise for you to see that if s is e to the I phi of x, as we have shown here, then s star gradient s will simply be equal to I times gradient phi. That's very easy to see. And now if I do this contour integral, it will tell me that this integral is equal to the value of phi at this end is just below where I started in this picture, minus the value of phi just above. Now you may think that, oh, that shouldn't that be 0? Not necessarily, because what you gave me is s of x. You did not give me phi of x. I just made that into a device and did this computation, right? But what we know is that e to the I phi of x e must be equal to e to the I phi of x. That has to be the same, because the field configuration is, the field is e to the I complex number, e to the I, it's the unimodular complex number, which at a point is the same. But if you do some excursion and come back, it can be represented in different ways. Because these two have to be equal, what this will show you is that the phi on just below here must be some integer multiple of 2 pi, that m is an integer, right? It must be only an integer multiple more than this, of 2 pi than this phi of s, and m is an integer. So what this shows is that this quantity has to be an integer. So you take any contour which is a which is a contractible contour on the torus. That means that, so I'm taking simple contours on the torus. For example, I'm not going around the handle of the torus. It's a contractible loop. You give me a contractible loop. What this shows is that this quantity which I'm defining as WC has to be an integer. Okay. This is called as the winding number associated with the contour C. Okay. So what is the lesson we have learned from here? Even though S of x, that is the complex unimodular complex numbers you have given me, are single valued, phi of x, the angle that you can use to characterize it, is not unique, may not be uniquely defined, in fact can be multi-value. What all this sounds like mathematics. What does this really mean? So let's understand this. So I talked about spin wave excitations, which are small, very small deviations about this uniform state that we had, right? The phi of x was small. And if you look at those kind of excitations, you will see that W of C is equal to 0 for any contractible contour C on the torus. So spin wave excitations are characterized by those configurations of S of X such that they are all their winding numbers on any contours will vanish. On the other hand, I can have excitations called as vortex excitations, right? And I can give you S of X in such a way that S of X is uniquely defined at every point, maybe except 1 or 2 points, but the phi is not uniquely defined. So here is one such configuration. So I just not worry about this point at the origin. You see the spin starts along the x-axis, x direction here. When I reach this 45 degree, it turns around and it turns around like this. So now if I do the process that I outlined, the contour, and if the contour encloses the origin, if the contour encloses the vortex core as it's called, then I will see that the winding number is 1. So winding number will measure the vorticity. So what is the argument that winding number is integer? It tells you that vorticity is quantized in the sense that it is integer numbers, right, in this picture. So this is the m equal to 1 vortex, this equal to m equal to minus 1 vortex, and this is m equal to 2 vortex, and this is m equal to minus 2 vortex. So I would encourage you strongly to kind of try to reproduce these pictures by yourself of how you can get this kind of vortex configuration. So now you see vortex excitations can be thought of as point excitations, namely how do you describe the existence of a vortex? You have to tell me where the vortex core is and you have to tell me the vorticity. So vortex excitation is characterized by its position and the integer which tells me how much vorticity is there. Vortices are what are called as topological defects. What do I mean by topological? So imagine that someone gave you a configuration in an infinite plane with a vortex in the center. Now you can convince yourself that you can move the vortex around from place to place by trying to rearrange the spins. But by doing something for finite, let's say that to change the configuration of any given spin, it will take you like 1 second. So what a vortex configuration means is there is no finite amount of time you can use. In any finite amount of time, you cannot get rid of this vortex. You can move it from place to place. But if you want to remove the vortex, it will take you infinite amount of time because you have to rearrange the spins all the way to infinity to get rid of this vortex. So in this sense, it's topological. If a vortex is there, it was there to start with, and right, so it can't be removed by nice smooth deformations of the spin. So this is why they are called topological defects. So you can ask me a legitimate question. I start off with the torus, how can I get this vortex excitation if I can't introduce a single vortex? So that's what I'm going to show you next, right? So like I said, a vortex configuration is characterized by the number of vortices which we call NV. You tell me the positions of each of these vortices, L going from 1 to NV, and the vorticity associated with each of these vortices. Now suppose you give me such a configuration, you give me NV positions and NV vorticities, that does not specify the excitation state completely. In fact, you can show that you can add spin waves to any given excitation and you can produce new excitations with the same vortex configuration. Second point is, I mentioned that you are starting with the torus which was in the ground state. How can and I said that you can't introduce a single vortex. So how can vortices show up at all? So here is a very nice way to see that if you are working on a torus, the excitations have to be such that the total vorticity have to be 0. How do we see that? It's actually a very simple argument. The idea is the following. Suppose this contour is such that inside this contour there are no vortices. I can certainly do that because any vortex configuration you are going to tell me which are the positions of this. So I am going to choose a contour which does not contain any vortex. So now when I do this integral, I am expecting 0 because there is no vortex inside here. But you see, this contour can be thought of as the boundary of the region inside or the boundary of the region outside it. Both of them will give you the contour integral of 0. So here the contour integral has to be 0 because there are no vortices inside. And because it's also the boundary of the outside, it means that the sum of the vorticity inside in the other region have to sum to 0. Otherwise you would have got a winding number. So that is what is telling you that the sum total of vortices on a torus have to vanish. We will also give an energetic argument for why that happens. So we'll continue with this. Okay. So this is what. So it has to be 0. So you can see that there's a lot of topological ideas that are coming into this. Okay. So now we are faced with a question. We know how to write energy of the spin wave configuration. That's very easy. Just take gradient of these guys and just sum over all this. How can we write the energy of a system with vortices? Okay. So now you see, if you are familiar with something like superfluidity, etc., you will see that this gradient of phi, which we have discussed when we are discussing the Ginzburg-Landau theory, gradient of phi is like the current associated with the superfluid. So you can imagine this to be like some kind of velocity square. So in some sense this is like the kinetic energy that is involved. So the idea is, since S is a unique field in the sense that S is a field which has one value at every point, S is this complex unimodular complex number, and phi is a field which does not, which can be multi-valued. What we are giving is gradient of phi, but phi is not a pure gradient. That's what phi does not, that is the vector field associated with the gradient of phi need not be curl free. So what we certainly want to do is, we want to write out some theory where, okay, so there is a j by something missing, j by 2 missing. We want to write down something like this, where u is the velocity. We are not saying now that velocity is simply gradient of phi. We are just saying that there is a velocity, and we are saying that the square of this velocity times j by 2, which is missing here, is the energy associated with this configuration. And how do I get the vorticity in? If I do the integral of this, I will get this winding number. And for example, if you give me this configuration of vortices, the u must be such that when I integrate over the contour, say that contains the x2 point, let's say, it will pick out, and if I just go a neighborhood of this x2 vortex and do as a contour integral, I will pick up m2 as the winding number. Okay. So this is what I want. So instead of specifying S directly to compute the energy, I am going to specify a vector field which characterizes the velocity of the superfluid, if you wish, associated with that S field, and I will just square the velocity, which gives me the kinetic energy, multiplied by j by 2, which is missing here, but it is there, and that will tell me the energy of this. But this is a bit difficult because now I have to integrate over all this velocity fields, etc. So here is where a very interesting idea from mathematics will help us. So we know that any vector field which formally now corresponds to the gradient of our angle can be broken up into a conservative piece or the gradient of some scalar field plus curl of another vector field. This is called Helmholtz theorem. If you write Helmholtz theorem in 2 dimensions, you will see that associated with every vector field, there are 2 number scalar fields, zeta of x and psi of x, such that ui can be written as gradient of zeta times its some epsilon. So if you take, so if I epsilon aj is the fully antisymmetric tensor, that means epsilon 1 2 is plus 1, epsilon 2 1 is minus 1, epsilon 1 1 is 0 and epsilon 2 2 is also 0. So it's called the alternating tensor. So what this tells me is that u1, the one component of u1 will be d1 gradient along one direction of zeta plus d2 psi and u plus d2 psi, and u2 will be d2 zeta minus d1 psi. So that's the parameterization. Okay, so this is the alternating tensor, and this is the definition of this vector. Okay, so what if we start off with psi equal to 0? Then this ui is curl free, and you can see that this velocity field looks like di of zeta. So zeta is simply a proxy for my phi, right? And you will see that any contour c, if I do the integral, I will get 0, and this is how you describe the spin wave excitation. So this piece describes the spin wave excitation, right? And this piece will describe the vortex excitations, as I will show you in momentarily. So take a system where say zeta is 0, it does not have to be, but for simplicity you can take it to be 0, and psi is not 0. So now if I take WC, the winding number around contour C, I just go through this algebra. So you will see that only this term will contribute. When I do this, only this term will contribute, and you can see that this will become del square psi. Now suppose I have a vortex sitting at some point and I start taking this contour around that vortex, then you will see that I will get the winding number is equal to the vorticity of that vortex. So if I keep shrinking this contour now around that vortex, this region will also shrink around, and as long as I contain that vortex, this number will still be 1, will be m is the vorticity of that. So that allows me to conclude that this minus del square psi is 2 pi m times the delta function located at that point. So here's the precise argument. If there is a vortex of vorticity m located at the origin, any contour however small enclosing the origin will have a winding number m. So if I now use this equation, it will force me to conclude that del square psi is equal to 2 pi m times delta of x. So this kind of psi will allow me to characterize vortex fields, right? So the psi associated with a single vortex of strength m located at the origin is this. And if you ask what is the velocity field associated with that, you can see that the magnitude of the velocity of field will die as 1 over r, and it will be sort of along the e phi direction if I go to polar coordinates in x and y, right? Now I snuck in something called as the core radius here. You will see what that is. So when I solve the equation del square phi is delta function in 2 dimensions, you will realize that there is a problem both as x goes to 0 and as x goes to infinity. The sort of Green's function diverges in both directions, and you need a scale to get a dimensionless number, and that is what is called as the core radius. Very briefly, what the core radius is, remember when I drew the vortex configurations, very near the central point of the vortex, I couldn't decide what the spin had to do, so I just didn't draw it at all. But you realize that there will be some energy cost associated within some region in which we don't touch, we don't ask in the continuum what we are doing there. So we sort of isolate that region and we call it the core radius, and this AC is actually the core radius. Okay. So this is the psi field associated with a single vortex of vorticity m located at the origin. What will be psi for if I have a vortex system given by nv vortices and the positions and the vorticity? Well, this is like a Green's function, so you just add them, right? So you center each around this xl and multiply them by the strength of vorticity and just do this, and you end up getting psi field. So now we have a way to characterize the velocities associated with vortices in a very nice way. Okay. So I can use this idea, and I can now, you can now go ahead and write this is u square, and when you substitute u is equal to this, you know, see, when I do this, I'll get the u associated with that, and what I will, when I use this formula, I will get the u field associated with that. So u square will be simply gradient psi square, that's what I'm using here, and I'm computing the energy. Now when I compute the energy, you saw that this will give you velocities which are equal to 1 over r square, so that's why I'm getting r square, 1 over r square here. There is the m square, there is this m square, r dr is simply the area element, and 2 pi is the angular integral, and you will end up getting this. So now you see something very beautiful. You see that I am only integrating from AC to R. R is the system size. Why am I doing this? Because you see, this continuum description is not valid below AC. So what I am going to do now is, I am going to phenomenologically say that I will get a core energy, that is energy associated with whatever I have sort of excluded, and we know that since this scales as m square, it is also natural to scale this core energy as m square, where m is the vorticity. So therefore, I find a very beautiful result that if I have a single vortex excitation, I will end up getting an energy which is pi times j, j is our coupling constant, times m square, size of the vortex, log of r by AC. R, remember, is the system size. So this is terrible, because it's telling you that you cannot excite a vortex because it causes a, the energy of the vortex goes log of the system size. So you may wonder why even worry about this, right? And EC is what is called as the microscopic core energy, which is not taken into account in the continuum. So very clearly, we cannot excite an isolated vortex because it will cost us very large amount of energy. We'll have more to say about this as we go along. That's one comment. Second comment is, you will see that you can excite vortices of different vorticity as we have seen. But since the energy goes as m square, the vorticity square, we will see that the only reasonable things that you will be able to excite are m equal to plus minus 1 vortices, because if you go to higher vortices, of course, you will run into trouble with energy, that is. Okay, so we have computed the energy of a single vortex. What would be the energy of our collection of the vortex system? Okay, this requires some calculation. We know the W associated with the vortex, the psi associated with the vortex. From the psi, we can compute the Ui fields, the velocity fields, and from the velocity fields, by integrating the velocity fields, we can compute the energy, and you will end up getting this very nice looking result. So what is the result? So there is some logarithmic dependence on the distance between the vortices, and there is the product of the vorticities. Then there is a term which sums over the squares of the vorticities and times E core, and this is just obviously from the previous formula there. And the more interesting result is, there is also a term which depends on the system log of the system size, and that gets multiplied by the total vorticity square. So now you see that if this term equal to 0, then I get something very nice. So this is like I pay some energy EC to create some vortex, and each of these vortices are interacting with the other vortices through this logarithmic function, this log of distance. So what are the key observations we can make? Excitations with total vorticity 0 will be favored. We already made that point. You can now interpret these vortices as charges with a logarithmic potential, right? So you can take this into some electrostatic problem. So what is the electrostatic problem specifically? So imagine that you had some molecule AB, that's a neutral molecule, right? The question is, if I put a collection of these molecules in 2 spatial dimensions, and let's say the electrostatics were also in 2 dimensions, and if I were to break this plus minus charge of this AB molecule and move them apart, then in 2 dimensions the interaction between them will be log. That's the Green's function of electrostatics in 2 dimensions. So this problem really is a problem of dissociation of a bunch of molecules in 2 dimensions. The question is, to break them up you need to pay an energy EC. This is like the binding energy of the molecule. And once you give them the binding energy, they break, but then they are charged, and then they will start talk to each other, and that's the energy, right? So this is exactly the problem of electrostatic problem. So this problem is called as the Coulomb gas in 2 dimensions. Okay. So now we have discussed the energetics of pure vortex configuration. For a general configuration including spin waves and vortices, what is the energy? Okay. So we know that any configuration S of R, the gradient of associated with this is called U of R, or S of X I should say here, so that's a typo, right? S of X, we can characterize it by this. So you will see that the velocity field can be written as gradient of zeta plus epsilon ij di psi. We know how to write zeta for spin waves. We know how to write psi for a given configuration NV of these vortices. This script NV, you have to specify the number of vortices, their positions, and the vorticity of each vortex. So once we do that, we can find the psi. And now what I hope I have convinced you is that if you give me any configuration, I can find zeta and psi such that I can describe the velocity. It's just Helmholtz here. Now comes the most interesting thing. Suppose I make dimensionless energy. So this is a simple redefinition. So because I want to exponentiate this in the partition function, I am dividing it by t. So this k is j by t, and E tilde c is whatever core energy divided by temperature. So you will see that there is a sum of gradients zeta and gradient psi here. So when I square this, you may think that there will be cross terms, there will be terms between zeta and psi. The remarkable thing is that they will not talk to each other. Spin waves and vortices do not talk to each other. In fact, the energy will be the energy of the spin waves plus the energy of the vortices coming from the theorem. Okay. I mean, one can physically argue why that is the case, but you should definitely take a shot at giving that explanation. As well, you should try to work this out by mathematics. Okay. So now we come to the final, all this hard work that we have done. We are now able to see that the partition function of this is a functional integral over the zeta over the spin wave fields, and the sum over all possible configurations of vortices, including no vortices, one vortex, two vortices, all of them. You just specify all possible positions and moment of this. So I am just formally writing it as a sum, So you might wonder, why can't I think of XL being a continuous variable? See, that's where you have to remember that there is some core energy, core scale. So you must imagine that the space is discretized by this core. So you want to think of these XLs as some discrete objects, and that's why we write it as sum. So formally, for any possible configuration of the XY model, we have at least some description of the energetics. That configuration may involve spin waves as well as. Okay, with all this developed, now let us see what is the physics when we are at high temperatures, namely this K, remember we discussed this as J by T. Suppose J by T is very small, so K is much less than 1. I want to characterize that phase or whatever state that is being realized there using my statistical mechanics that I know. So what I am going to do is, I am going to look at what is the correlation between the complex number, unimodular complex number at origin and something that is some R lattice spacings away. So R is an integer far away. So what do I need to compute? I need to compute I need to take this product and find its expectation value. So that will tell me the correlator between these two. And I take the real part of it because a priori this is, it looks like a complex number, but you will see that the answer is real. Okay, now if you are at high temperatures and you can take the lattice picture itself, then you will see that this computation is actually very easy and it looks like the Ising model computation which we have done before. I will go through this briefly. So if you look at this product, so that is between two lattice points which are R apart. Now what you can do is, since it's a product of these two things, I can add a whole bunch of ones which are ones added on all the lattice points that are in between these two. And each of them I can write it as S at that point and S star at that point. So when I do that, you will see that I will go from all lattice points from 0 to R minus 1, and I will end up getting the difference of the theta between the neighboring lattice points. So when I add all this, when I take the next site for if I am at I, if I go to I plus 1, I will get a term with this thing will become plus e to the I theta by I plus 1, and that will cancel this complex number out. So ultimately the answer will be this. So what I end up seeing is that this quantity is go through the line connecting these two points at 0 and R, and you just see that is simply the product of e to the I difference of theta on each of these. So what is the advantage of doing this? The advantage of doing this is that we know that at high temperature, each link will do its thing because each link will be unconnected with another link, and each link will do its statement. So what I can do is I can just find this quantity, and I need to do the expectation value of this quantity, and I just take product because they are independent random variables. So when I take a product, because the probability goes as e to the k cosine theta, that's from the first slide, the cosine of delta theta, the sine part of this will die because that's an odd function, and I'll just end up with cosine delta theta, and this is a bit of algebra, so you will see that when you do this integral, it will turn out to be some Bessel function, and so you take the log of some Bessel function, and if you work this out as k goes to 0, this will turn out to be k by 2. And so since this is k by 2, you can conclude therefore that this correlation function goes as e to the minus r by c, the distance by c, where c is the correlation length, and this correlation length you see now goes to 0 as t goes to infinity. Okay. So this is the result, that you are going to this paramagnetic phase with 0 correlation. So it's like exactly what we expected. Okay, so at least we learned some techniques of how to do this calculation, but physics wise I think we could have guessed this even otherwise. So high temperature phase is a short range correlated paramagnet. So this is the result that. What happens when k is much greater than 1? When k is much greater than 1, we can neglect vortices completely, because vortices are very expensive. The core energy is already there, and if you work at temperature scales which are much smaller than the core energy, then all of their effects are exponentially suppressed. And I do have gapless excitations in the system, so they will be all excited, right? Because a gapless, at any temperature, some of them will be excited. And so what I can do is I can try to find this correlation function, which is now just the zeta part, because remember the u is gradient of zeta, so zeta can be thought of as the angle itself. So I have to compute this, and remember h spin wave of zeta is like a Gaussian. So this is like finding expectation value of a Gaussian distributed variable, and there is a beautiful theorem you can easily prove. Expectation value of E of x, E of ix, where x is a zero mean Gaussian, it looks like e to the minus 1/2 of expectation value of x square, right? So this is actually it's all coming from the fact that the Gaussian has only one cumulant, okay? So it just comes from there, and that is what you will find. So you use that idea, and after a bit of calculation, I am not showing you all the details because it will take us a bit of time to show all the nitty-gritties, but please work this out yourself. You will be able to show that this quantity, which is what I need to compute this, goes as 1 by pi k log of x minus x prime by a, right? This is what I will find. So now what is the expectation value of this? It will be e to the minus 1/2 of square of this. So when I do that, I will end up getting this result. Just stick it in here, and you will see an extremely beautiful result. You will see that things at 2 points are correlated as a power law. Just work out exponential of log will give you this power law. And so you will see that it's a divided by the distance of this. So you see that these are power law correlated. And what is more interesting is that the exponent of this power law is temperature dependent. And when t goes to 0, this is 0, which means that this will be 1, but that's exactly the broken symmetry state. So you start from this broken symmetry state where everyone is stuck in the same direction, and you start, there is going to be some power law dependence. So you have a very interesting phase which is gapless and whose correlations are changing as a power law in a temperature dependent exponent. Okay. So this is the state which is called as algebraically ordered, which means this is a power law, that's why it's called algebraically ordered, with a temperature dependent exponent, and this kind of state is called as an algebraically ordered state, and it occurs in a regime of this parameter temperature. Most interestingly, we see that there is no broken symmetry. Of course there shouldn't be, because Mermin-Wagner theorem will be violated. But Mermin-Wagner theorem tells you that you can't, so what it tells you is that this can't have a finite expectation value at infinite distance apart. Right? If you had that, then you would say there's broken symmetry. It goes to 0 when distance goes far away. So there is no violation of Mermin-Wagner theorem. But Mermin-Wagner theorem does not disallow you power law correlated states, right? And therefore, this is well within Mermin-Wagner theorem, and you get this very nice power law correlation. Okay. So now there is a very interesting puzzle which we have to address. So we know that at low temperatures there is this algebraic order, and at very high temperature there is a parameter. The very natural question to ask is, how can an algebraic order go into a parameter? How can a power law become an exponential? Something has to happen. Well, if that something is something like a first order transition, well, that's possible, we don't know. So maybe to find the answer to this, you need to get a beverage for yourself so that you can stay fresh. Okay. So now the, just common sense will tell you that this can't be smoothly connected to this. See, there's probably some kind of transition that is going to take place. So Kosterlitz-Thouless and shortly before them Beresinski, they argued that the vortex excitations, remember we completely neglected vortices to get this algebraic order. The vortex excitations have a crucial role to play in taking you from this algebraic order to this parameter, right? And they gave a very simple argument which, if you want to try it, you can pause the video and try it yourself. I'll give you the hint that it looks like the 1D argument of the 1D argument. By that I mean the argument that we gave to show that there is no ordered phase at finite temperature in the 1D Ising. Okay, so let me show you what this is. So you know that if I take the m equal to 1 vortex, the energy associated with this vortex is pi j times log of r by ac plus e core. Sorry, I missed out the e core. So I don't need that for now, but I missed out the e core here. Now you can ask, okay, I'm introducing this single vortex. I pay this energy, but I may gain some entropy. So what is that entropy? So imagine that I have a system of radius, very big system, radius r, of system size r. So the area of that is pi r square. Now the vortex, remember, has some core radius a, right? So that area will go as pi a square. So the number of ways of being able to place this vortices, the single vortex in this area goes like pi r square by a square, right? I'm just counting how many little pieces of AC square are there in r square area. So that will give me a number, a big number, and you will see that the entropy is simply log of this number, and you will see that's 2 log r by AC. Okay. So now I know the energy associated with the excitation of a single vortex. I know the entropy associated with the excitation of single vortex. So I can go ahead and compute the free energy, which is E minus Ts. Okay, apart from some small core energy, which you will see I can drop because of there is a log r here. You will see that this is pi j minus 2T. So now you see when temperature exceeds pi by 2j, then I see that single vortices can just proliferate, right? So vortices will start to proliferate above this Tc, which is pi by 2j. And once vortices start to proliferate, then of course this spin wave and all that stuff is completely destroyed. In the sense, I mean, there are much bigger excitations. So it can actually destroy this algebraic order. The question is this crude picture correct? And so what Kosterlitz and Thouless did is, believe it or not, they use renormalization group to answer this question. So how did they use the renormalization group to answer this question? So the idea is the notion of vortex pair unbinding. So let me try to explain to you the qualitative physics of what they thought could be happening to drive this transition. Since the energy of the vortices scale is m square, the first argument you will use is to say that I will be only worried about m equal to plus or minus 1 vortices. We already made this point before. So again, think of some AB molecule which is dissociated. So they are the charges. So what this means is that if I start with vacuum means the state with no vortices, I can only excite vortices in plus minus pairs if I want to make Gibbs happy. That is the weight, thermodynamic weight associated with that, otherwise it will scale as log r. So now if they are separated by a distance r, their energy will go like this. This is the state, right? A pair times E core, right? So what this means is that smaller dipoles are likely to be excited, right? So that's the idea. So they will want to have a smaller dipole like excited. The question is the following, right? So I want to excite a dipole of certain size. Dipole meaning a pair of vortices. Now smaller vortices would have been smaller dipoles would have been already excited because they have lower energy. So what will happen? What will happen is that this quantity, the existing small dipoles will screen the interactions between charges associated with the bigger dipole. So having a population of small dipoles means that the dielectric constant on a larger scale changes, contributing from the induced dipoles at smaller scales. Okay, so this is the point, right? And this is exactly the idea. And what ends up happening is that the smaller dipoles, they screen the interaction between the charges associated with the larger dipoles, and it will change the dielectric constant on larger scales. It will increase the dielectric constant on the larger scales. The question is, can this process go on and on and on? So if I start increasing temperature, I start developing a small population of very small tightly bound dipoles. But once I have that population, slightly longer dipoles will become, it becomes easier to excite, and so on. So can this run away, and can it come to a point where the dipoles will unbind because the largest dipoles can be excited easily? So this is the question. Can it lead to unbinding of dipoles, in the sense that once the vortex pairs unbind, then it will be like free gas of free vortices. Okay. So what do we need to understand now? So we need to understand, for example, we have to understand the physics of a dielectric medium. Dielectric medium in the sense that if I want to do electrostatics, I can do it in vacuum, which means I bring some external charges in the vacuum, and you see the charges will just interact with each other. But suppose I have a dielectric medium. When I bring external charges, I will induce new charges in this dipole. For example, the smaller dipoles that we have, I will induce these new charges, which means the interactions between the charges that I am bringing externally will change. So how do we model that? So let's start with the Poisson equation. The Poisson equation tells me that the potential is related to the charge density by well-known elementary result. This is Poisson equation, and it's very natural to think in terms of Fourier space, because what I'm interested in long wavelengths. So I would like to go to k's that are small. K is the wave vector that are small. So I naturally adopt the Fourier language. So Poisson equation in Fourier space can be written like this. So V of k is 1 by k square, that's just coming from the gradient square, right, is the Fourier transform of the Coulomb potential. So what this is telling you is that the potential associated with a charge density. Okay. Now suppose I have a dielectric medium. The question I want to ask is, I bring an external charge into the dielectric medium, what is the potential I will develop? So that potential is written as this Coulomb potential, this Coulomb field, right, this divided by the effective new dielectric constant of this system. This Ek is a property of this dielectric medium. How do we compute Ek? That's the question. Okay. So to compute this effective dielectric constant, what we do is we will note that the charges will be induced. How will the charges be induced? Well, associated with this external charge density, there is an external potential that is given by just the usual Coulomb kernel, this one. It will give me, it will induce some external charge, this external charge will produce this potential. And chi k is a susceptibility of my dielectric system. If there is an external potential, it will produce an induced charge rho I in the dielectric, right? And this I am now connecting, the external potential I am connecting to the charge that we have brought out from externally, and that is just the Coulomb kernel divided by epsilon naught times that's just this, right, times rho e. So what is this chi k? It's the charge susceptibility. And what do? We take this now and say that the total potential is the external potential plus induced potential. And after a little bit of algebra, we are able to connect the effective dielectric constant of this dielectric medium 1 by Ek to the dielectric constant of vacuum times some property of the medium, which is the charge susceptibility. Okay, so this is the most important result. Okay, and what is the long wavelength or the long distance effective dielectric constant? So 1 by epsilon, so I am taking k going to 0, that is what this quantity is, will be written like this. So I have just rewritten what is V of k, etc. And this is the result that, okay. So now you see we have to change our, because we know that the dielectric constant is going to change. You see that this J0 in our problem plays the same role as 1 by epsilon 0. So J0 is like the inverse epsilon 0 of the electrostatics. So we have to now distinguish between what comes out, the effective potential of the dielectric system from J0. So we will call this as J0, which is the original J we had in our in the Hamiltonian, if you wish, and this J is what will show up after we allow for vortices to come in and they changing their the smaller vortices screening the larger vortices, etc. Vortex pairs is what I meant, right? All right. So now, if you go by analogy, you compare the electrostatic equation we wrote on the previous slide and the equation for W, etc. that we wrote down, you can show that effectively this 2 pi square J0 looks like 1 by epsilon 0, and the long wavelength J is related to the short wavelength J by exactly this result. Okay, so that's the result. So you just got some factor of 2 pi square, it's not very important. Okay. Now the question is, how am I going to compute this chi k? How am I going to compute the susceptibility of? So in the context of electrostatics, it's charge density. You remember susceptibility will be like density, charge density correlator. This is exactly Kubo formula. A, B correlator divide 1 by temperature, expectation value will be the susceptibility. So that's exactly this result. So it's minus 1 by T, mk is the density of vortices, Fourier transform of, and m minus k. So you can see that mk is given by the Fourier transform of the vortex density, and vortex density for a given vortex configuration with where vortices are sitting at positions xl, with each having vorticity ml, is this quantity. So you can stick that in here, you can find the Fourier transform and you will get this nice result. So I have this expression and let me do some statmech with it. So what I really need is I need chi k divided by mod k whole square. That's what I need. So what I do is I try to go for the jugular by directly trying to find that quantity. So you see I do 1 by mod k square and I take mk and m minus k and I use this definition and I expand in k here. Okay, this is a bit of algebra, but you can easily do it. So when I do this, I'll end up getting this. Now the leading term of this will turn out to be the total vorticity. So this will go to 0 and this will turn out to be 0 as well, because this is integrated over x and x prime, but x and x prime are dummy variables, and if I switch the dummy variables, this will pick up a negative sign. So something is equal to negative of itself means it is 0, and that means the leading contribution will come from this term, right? That's the term that will give me the leading contribution. So you will see that this quantity is exactly this. And I have done some simplifying algebra. So why this 1/4 shows up, etc. You have to work out the component wise and so on. So you'll get a k alpha, k beta, and all this. So I will not belabor those points here. So please work this out yourself. You figure out why do you get 1/4 here. So in all this, A is the area of our system, and it's introduced so that all this Fourier transform and all these etc. things can be done nicely. So ultimately, what we are finding is that the effective J of the system associated with the vortices, or the fact that there are all these excitations of vortices etc. there, what is the effective J? That turns out to be equal to J0 plus pi square J0 by T times this quantity, where this expectation value is computed in the XY model's ensemble. So you will see it looks like some kind of mean square size of the dipoles. That's crudely what it is. If there are some signs involved, etc., but that's what it is. Okay. So now we want to go to dimensionless language. So what I do is I divide everything by t here. I divide it by t. So this becomes k, and this becomes k0, and this is pi square k0 square k0 times this. So now if I remember that m of x is sum over all dipole positions etc., you can see that I can rewrite it like this very nicely. So I see that k, the effective k, is k0 plus whatever I got by screening etc. So like I mentioned, this sort of becomes like some mean square dipole length is what we are trying to compute. Okay, so now to do this computation, you have to work through some math here. So I do 1 by a expectation of this, and I am going to make a couple of statements. First is, I am going to assume that I am working in a temperature scale where what is called as fugacity y of these vortices is very small. That means the core, we are working at temperature which are much smaller than the core energy. So this y quantity is very small. So what I want to do is, I want to find this in a power series in y. I want to find this an expansion y and keep the smallest powers of y in. So naturally, the smallest power of y will be y square, because I need to have at least 2 vortices to have 0 vorticity condition. One has to be plus and one has to be minus. So in fact, that will be the smallest order term, because the smallest number of pairs of vortices that I can excite is 1, which will have 2 vortices. And now I simply do the stat mech of that. I simply find the this is the thermodynamic weight associated with that having 2 vortices, and that's pretty much it. And then you can write down all the information that you need. So this is x1 minus x2, that is exactly this, and I just do this integral. And after some algebra, you will end up getting this quantity. So this is minus 4 pi times this is y square times this integral here, AC to R. Now, if I am at low temperatures, then this K0 will be very large. If K0 is large, then 3 minus 2 pi times K0 is definitely negative. That means that R goes to infinity, this is well bounded and this is a convergent integral. So what I can do is, if I am at low temperatures, I can run this to, I can rewrite, instead of R, I can write it as infinity. So I will assume that I am at low temperatures, and let me, my point is I am going to assume that 3 minus 2 pi K0 is a negative number. Okay, fine. So now after all the discussion, so we have come to this stage, and to order y square, I see that k and k0 are related in this fashion. Now what I can do is, remember I am interested in the dielectric constant, so I have to take the inverses of these things. So I take the inverse of this thing and I sort of invert this equation if you wish, and you will see that I will end up getting this result, where I have replaced k and k on this side and made it as 1 by k0. 1 by k0 is my UV, an ultraviolet value of J0, J0 by T. So you see there is another motivation for doing this. The other motivation for doing this is that 1 by k has exactly the same meaning as G of the nonlinear sigma model. So we are now sort of writing some change of G kind of thing. Alright, so now what we have found is, we have found what is the effect of all these vortices on k, and we have related the effective k to the k, the bare k, the k that we started off with in the ultraviolet. So now it's RG time, so we can do renormalization groups. So now imagine that I think of the core radius that I have as lambda inverse. It's like the inverse cutoff. So I want to reduce lambda, you see. So what does that mean doing for A? I have to increase A. So I go from A core to S times A core. So this equation will remain unchanged. So basically I change K of S and I change fugacity, because fugacity's core is e to the minus core energy by T. So that quantity is dependent on the cutoff. So I change that. So that is also a function of S. And this is all changed to S like this. So in a sense, this has given me the renormalization group transformation Rs from Ky to K of S, Y of S. Okay. Now what I can do is I can do some analysis and I can figure out what should be Y of S and K of S, etc. Okay. In the interest of time, I will quickly show you from this Rs transformation what renormalization group equations we obtain. So the flow equations of that will turn out to be d by dl of 1 by kl is 4 pi square y square, and dyl by dl is 2 minus pi kl yl. So these are called the very famous Kosterlitz-Thouless RG equations of the x-y. Okay, very good. So what are the fixed points? So I have to set this equal to 0. So when I set this equal to 0, the first equation will tell me that YL has to be 0. This is the state where e to the minus EC by T is 0. What does that mean? That means the core energy is like infinite. That means I don't have vortices. So the statement is that the only fixed points are systems which don't have vortices. Okay. So there is a line of fixed points for any value of k. This is a fixed point, but remarkably something fantastic shows up. This line of fixed point, a point on that line is stable when this quantity is negative. So when k is greater than k bkt, which is 2 by pi, remember pi 2 by pi? When it is greater than that, that means you are at temperatures less than pi by 2 times J. The fixed point line is set of stable fixed points. Okay. So this is that line of stable fixed points. K is greater than k bkt of 2 by pi. So here all these points are stable fixed points. That means if I start with some finite fugacity, as I look on longer and longer length scales, it looks less and less dielectric, right? It looks as if it's more and more vacuum. That means there are no vortices at all on the larger scales. So it goes ultimately on the longer scales, it looks just purely spin wave. And then our results for the algebraic order of the spin wave is exactly true. And then you will see that this line of fixed points as a function of this, as you know, as I'm going in this direction, temperature is going down to 0 because K is inverse of temperature. You will see that you will get that correlator which goes as 1 by R the whole power something T by J or something. So that is the result. So you will see that this algebraically ordered phase is stable. Now when K is greater than KBKT, sorry, I mean when K is less than KBKT, which means T is greater than TBKT, right? You will see that, and BKT is exactly pi by 2J, that's exactly this result. Beresinski Kosterlitz-Thouless transition temperature, and remember we did some crude calculation, we found pi by 2J, and we did fancy RG to come to this result. You see that any amount of fugacity is irrelevant. That means if I have a little bit of vortices may start out to be very expensive, but on the largest scales, the entropy gain associated with having all these vortex excitations simply beats that energy penalty, and self-consistently the vortices will unbind and they will go into this plasma state of, the plus minus charge will become free, and that is this. So the paramagnetic state is somewhere out there, right? So all vortices become free and it just goes. So now comes the question, what happens at this point? That point is the point where you have the Kosterlitz-Thouless phase transition. So you go from this algebraically ordered phase to the paramagnetic phase. Okay. In fact, just a small tidbit here. If you are in this regime, right, this regime, so if your initial fugacity and the K naught were in this regime, in the blue regime, you will always flow into this algebraically ordered phase. If you are anywhere else, you will flow to the parameter. Okay, let's discuss a few things about the BKT transition. So the BKT transition is a very special kind of transition in the sense that it is brought about by the proliferation of topological defects. So we have this transition point which has some very interesting properties. In a short period of time, we will not be able to discuss how we derive, how we come up at to come to the results. You have to take the RG equations and analyze them. And I would refer you to papers by Kosterlitz and Thouless, the original paper, as well as a paper by Kosterlitz and Nelson to sort of get to some of these results, right? But the important points you will find is, at BKT, at the transition temperature, there is a jump in the effective stiffness. So what do we mean by this? We have to understand this carefully. BKT itself is not a universal number. BKT transition temperature is determined by J. J can be anything, right? The systems you can make up systems with different J's. But the remarkable thing is, just above that BKT transition temperature and just below the BKT transition temperature, there are these values of effective values of J you can get, and the ratio of that is universal and is equal to 2 by pi. And this has been seen in experiments on superfluid thin films, etc. At the critical point, if you analyze the renormalization group flow, you will see that the correlation function has a spectacularly interesting looking form. Okay, so you can see that this critical point that we have is very different from the conventional critical points that we are used to, right? So these are some of the properties of this Kosterlitz-Thouless transition. Now you might, if you are coming from more high energy physics or field theory background, you might find that our derivation of this RG flow equations were a bit too physicsy, in the sense that we did dielectric constants and all that stuff. So in fact, there is another way to come to the same RG equations by using exactly Wilson's method of introducing a shell in the momentum space, integrating out the fluctuating modes, fast fluctuating modes. And that goes like this. I'll briefly mention this. You can try this yourself, or you can read some literature. So what you can do is you can start, you know that all physics is there in the HV problem. HV is the problem, the energy associated with the vortex configuration. So you can show that this Coulomb gas, namely the question of, there is a energy associated with popping charges out of vacuum, which means like dissociating molecules. And them interacting with this Coulomb-like potential. You can map that problem to a continuum field theory called as the Sine-Gordon model, right? So the Sine-Gordon model roughly will look like this. There is a field called phi. The energy will go as gradient phi whole square. It will look like our Gaussian theory, plus something times cosine of phi, and that something will be like the Fugacity kind of thing that we have. So you will see that when you work that theory out and do renormalization group, you will see that you will recover all the results that we have in our discussion. After this, you will be able to see a more deeper connection if you think a little bit more. You see, this problem we are discussing is in 2 dimensions, and we have also connected with the 2-dimensional Sine-Gordon model. But the 2-dimensional Sine-Gordon model is actually some thermal or some ground state problem of a 1-dimensional classic, a 1-dimensional quantum problem. Sorry. So the 1-dimensional quantum problem will map to the 2-dimensional Sine-Gordon model by our D quantum connecting to D+1 class. So now you realize that many phase transitions of these 1D systems with continuous symmetry will turn out to be BKT like, right, with some U1 symmetry, etc. U1 symmetry is like, there are many systems with U1 symmetry in 1 dimension. So they will have transitions which are like BKT like, quantum phase transitions which are BKT. So you see that this BKT physics will have a lot to say about systems in low dimensions, not just in 2 dimensions. So we have seen a lot of things in this lecture. So let us summarize what we have seen. So we have seen that nonlinear sigma model with ON symmetry allow us to explore physics in near 2 dimensions. We see that all the results are consistent with what we know from other considerations, and we have also recovered the Mermin-Wagner theorem kind of results. So systems in 2 dimensions with O2 symmetry are very special. They have algebraically ordered gapless phase at low temperatures with exponents that change continuously with temperature. They have special types of excitations called as topological defects. They can proliferate and destroy the algebraic order through a very interesting new kind of continuous phase transition called as the BKT transition. BKT physics also appears in quantum systems in 1 dimension. And ultimately, BKT physics, I would say, is a fantastic illustration of the renormalization group. So you can see that, how we started off with some microscopic model and started looking at what is the physics on longer scales and so on. Exactly as prescribed by the renormalization group, we were able to discover the physics of this continuous phase now. Okay, we have a few more lectures left in this course, and what I'm hoping to do is to introduce you to some more research oriented topics such as quantum memories and neural nets and so on. So I hope you will join me for those discussions. Thank you very much. Have a nice day.